As I've said before, we loosely say that capacitors store charge, but really they don't store charge, they store energy. We do work separating the charges between the plates, and the work done is stored in the capacitor as potential energy. So let's figure out how much energy is stored in a capacitor. The potential energy stored in the capacitor is 1/2 Q delta V. You might be thinking, why 1/2? Isn't the work done in moving a charge through a potential difference Q times delta V? Shouldn't this just be Q delta V? And the answer is that we didn't move all the charges through that whole potential difference. When we moved the first charge between the plates, we did no work because we weren't fighting any charges that were already at that location. When we moved the second charge, we had to do a tiny bit of work because we were pulling an electron off of a plate that was positively charged. So we had to do a little work there. And we pushed it onto a plate that already had an electron on it. So it was repelled by that electron. So we had to do a little bit of work. And the third charge, we had to do a little bit more work because we pulled the electron away from a plate that had 2 positive charges attracting it. And we moved that electron around and put it on the plate over here that already had 2 electrons. And we kept moving charges, and we had to do more and more and more work. So the very first charge, the work done was 0. And the very last charge, the work done was the charge times the potential difference delta V. And when you average it all out, over the whole course of charging this capacitor, moving all the charges over, you get 1/2 times the total charge times the potential difference. Now, we can also write this in other forms because we know for any capacitor, the charge stored is proportional to the potential difference. So I can make some substitutions here and write this as Q squared over 2C or 1/2 C delta V squared. These are all equivalent forms for the energy stored in a capacitor. Let's do an example where we have to use our rules for series and parallel circuits. They're pretty powerful. We can take a fairly complex circuit and reduce it down to a single capacitor, find the charge and the potential difference across that capacitor, and then work backwards, step by step, and figure out the charge and potential difference across every capacitor in our circuit. And that's what we're going to do with this example. Now, in the last video, we found the equivalent capacitance for this circuit, so I'm not going to do that again, but that's where I'm going to start. I would take this complicated circuit and reduce it down to a single capacitor if I could, and I can in this case. And then I work backwards, filling in all the blanks as I go. Last time we found the equivalent capacitance for this circuit, and if I plug in the numbers I gave you in this problem, it comes out to a 1 farad capacitor for the equivalent capacitance. So how much charge is stored? I'll call that Q equivalent. So the charge stored is 6 coulombs. One thing that can be a little confusing, we use capital C often to indicate a capacitor. I think I've done that already. C1, C2, and C3 for capacitor 1, capacitor 2, and capacitor 3. But the unit for capacitance is the farad, and the unit for charge is the coulomb. So if we use C for coulomb, here it indicates that it's the unit for the charge stored on the capacitor, 6 coulombs. Now that I know the charge and the potential difference across my equivalent capacitance, how much is the potential difference across this capacitor? It's just the potential difference from the battery, 6 volts. Now I can work backwards. This equivalent capacitor really stands for 2 capacitors in series. What do we know about capacitors in series? We know the total charge on each capacitor is the same, and it's equal to the total charge stored. So Q1 is equal to Q equivalent 1, and that's equal to 6 coulombs from above. If I know the charge and I know the capacitance, I can figure out the potential difference across each of these. In this case, the voltage split equally because the capacitance was the same on each of these capacitors. We applied 6 volts to the 2 capacitors. Because each has the same capacitance, it split equally, 3 volts across the first and 3 volts across the second. If the capacitances were different, then the voltage would split differently. But this is how we would find it if that was the case. In this case, we found that they were equal. So we can take another step backwards because C equivalent 1 is really made up of 2 capacitors in parallel. Now I'm back to my final circuit. I've worked all the way back to my original circuit, and I need to figure out the charge on C2 and the charge on C3 and the potential difference across each one. Let's start with the potential difference. I'm going to scroll back up to my previous circuit, and I found that the potential difference from A to B across my equivalent capacitance was 3 volts. So where are points A and B on this circuit? They would be right here. The potential difference across A and B is 3 volts. And the potential difference is the same on every capacitor in parallel. So that's equal to the potential difference across capacitor 2, and it's equal to the potential difference across capacitor 3. So I know the potential difference on each of those. Now I can figure out the charge stored because I know the capacitance of these. They're each 1 farad. Q equals C delta V. Three coulombs. And if I look at the potential difference across 3 and multiply it by its capacitance, I get 3 coulombs. And if we add those up, that should equal the total charge stored on the equivalent capacitance of these two. So Q2 plus Q3 should equal Q equivalent 1. 3 plus 3 is equal to 6. So that checks out. Now this was a fairly simple circuit, but you can take very complex circuits and oftentimes reduce them down to one equivalent capacitor. And when we get to resistors, we can do the same thing. We have rules for series and parallel resistors. We can take a complex circuit of resistors, reduce it down to one equivalent resistor, and then slowly work our way backwards and find the current and the potential difference across every resistor. In this case, we're doing capacitors. We're finding the charge and the potential difference for every capacitor. Now, we can't always reduce the circuit down using series and parallel rules, but oftentimes we can. And we're going to learn some new techniques soon for those circuits where we can't apply series and parallel rules.